Uh, Hello there, this is exercise 3b, another look at matrices and how we can use them. And one way we can use them is to transform 2D shapes. And you may recall at GCSE you got asked to transform, like, reflect a shape or rotate a shape or enlarge a shape. A variety of different types of transformations you got asked to do on very often simple 2D shapes on a graph, basically. And the rules for those transformations are governed by matrices, so we're going to see how it works today. Let's have a look. So, little starter for you. Can you multiply those together? You can try to do them on your head if you like, or you could just cheat and do them in the calculator. It might actually be easier to just do them in your head, but I'll leave it to you. Pause the video and then we'll come back to me. Okay, so here are the answers according to me. The first one is 8, 1. Second one is 18, 8, and the last one is minus 7, 11. Hopefully you got those right. Now we do need to do that because effectively this thing, this first box, you can think of this as the transformation. And what we are doing is we're timesing it by this. Well, this is like a coordinate almost. It's only one coordinate. It's like that would be like 4, minus 3, I suppose. But we're doing some kind of transformation on 4, oh, I don't know why I said minus 3. It's 4, 3. But you're doing some kind of transformation on 4, 3, and it turns out that with that transformation it became 8, 1. That's what we're looking at today. And I suppose it's what kind of matrices produce interesting transformations, because 4, 3, 8, 1, I have no idea if that's interesting or not. But there are some that are interesting. So let's have a look at what happens. Firstly, we're going to need to define what I'm going to call the unit square. The unit square then is essentially the square that goes from 0, 0, goes across to 1, up to 1, 1, and then across to 0, 1. And you get this nice square, or it looks like a rectangle. It looks like it's been slightly stretched, but you get the idea. And we are going to write its coordinates down. There they are. So you'll need to make good notes of this. So, and then we put them into a matrix. And in matrix form, you can see 0, 0, 1, 0. 1, 1, 0, 1. And you'll notice basically I do this one, then this one, then this one, then this one. The last one is 0, 1, having gone round there, and you get eventually to there. And so, having labelled my matrices, I want to know what happens if it's multiplied by any old matrix. And I've suggested this one. This one says 0, minus 1, 1, 0. And what will happen to that? And you don't know until you do a bit of timesing. So let's do the timesing. Here's my matrix again. 0, minus 1, 1, 0. So this is my transformation. And this is my unit square. And you can see I'm going to times them together. So let's see what we get. We get 0 times by 0, and that times by 0. That's obviously going to be 0. 0 times by 1, and that times by, that's going to be 0 again. And eventually, I suppose, I'll get a minus 1 there. So we're going to multiply them together, and that's what I got when I do it. I'm sure you can type it in and get an equally, similar answer. And I suppose what now begs the question as to what does that look like if I put it back on my picture. So if I draw my axes again, you can see 0, 0. I start there again. My next one's 0, 1. It goes there. Minus 1, 1, minus 1, 1. That's that one, and obviously the last one's that one. So I suppose the question is, what has happened to the blue square to get it into this, well, purple square? And just on first glance, it could be a reflection. It could be a line through there. It could be a rotation, almost rotated, a bit like my arrows suggested. Or it could even be a translation. I picked it up and I've gone, and I've just plonked it down over there. So it could be any of those things, and it's probably easier to see what's happened if you use what I'm going to now call the unit triangle. And by seeing the unit triangle in action, it's easier to see. So you'll notice there's one less coordinate, 0, 0, 1, 0, and 1, 1. I've got this one up here. So I multiply them together, I get this, trust me, or do it yourself, I don't mind. And if I draw them, I get that. And then you go, oh, hang on a bit, that is definitely a rotation. In actual fact, it's a rotation by 90 degrees in an anti-clockwise direction. So we need to describe all of that as rotation. Technically, the center of my rotation is this origin, 90 degrees anti-clockwise. And so there's lots of different transformations which are interesting. The one I've just done is this one. Okay, that's the one I just told you about. But there's others, and you're meant to know these, and unfortunately, you're meant to know them off by heart. So I'm going to ping them up. I would suggest you copy these into your notes and make sure they're good notes that you've got. So this is the reflection in the x-axis. Now look, just look at that and compare it to this. This was 0, minus 1, 1, 0. So this one here was 0, minus 1, 1, 0. Let's just make sure I've written that right. Yes, I did. And notice this one I've got coming in, 1, 0, 0, minus 1. They're almost identical. Well, they're the same numbers, just in a different place. And that's the problem with all of these. They're the same numbers in a different place. It's just a case of are there pluses or minuses involved. There's the one I just wrote down. But notice there wasn't much difference for anti-clockwise and clockwise. Just the one of the where the minus is changes. And that's 180 degrees. And you're meant to know these, so your job is to learn these, because that's a pain in the bum, isn't it? But yeah, there's no way around it. You're going to have to learn it. So a bit like you would learn, I don't know, in 1066, the Battle of Hastings took place. You're going to need to learn that the reflection in the x-axis is 1, 0, 0, minus 1. Unlucky. Successive transformation. So what happens if a shape gets successively transformed? So use matrices to find the image of the point 2, 3. So I'm already writing 2, 3 down as a matrix like that. After it's been transformed by rotation of this, followed by this. Rotation of 270 degrees anti-clockwise. So I'm just thinking to myself, 270 degrees anti-clockwise. I reckon it's the same as 90 degrees clockwise. So that's what I think that one is. So let's just go back. 90 degrees clockwise is 0, 1, minus 1, 0. So 0, 1, minus 1, 0. So that's going to happen to it. And then after whatever answer I get from this multiplication, it's going to be followed by the reflection in the line y equals x. So let's go back to y equals x. Where's y equals x? Oh, it's here. And that's a 0, 1, 1, 0. But notice the way I'm going to do this. 0, 1. Was it minus 1, 0? No, 1, 0. Notice why I've done this. This is the first one that happens. And this is the second one that happens. How weird is that? You go backwards because this happens first. So I'll find out the new coordinate and then this happens to it. So I'm going to ignore the 0, 1, 1, 0. I'm going to do this. I'm going to say that's nothing. That's 3. And that's minus 2. And then when I do this, that's minus 2. And that's 3. And so minus 2, 3. Notice it wants the image of the point, which is the point is a coordinate. So I bet they give a coordinate to finish with. So notice how really I've got to change that to minus 2, 3. Here's another one, a backward transformation. Point P is rotated 180 degrees about the origin. So I don't know what P is. I don't know. I'm tempted to write AB. So 180 degrees about the origin. So this is where your good notes, 180 degrees about the origin, is minus 1, minus 1 on the diagonal of 0, 0. Oops. Minus 1 with 0, 0. The final are followed by a reflection in the y-axis. Let's go and find the reflection in the y-axis. Well, that's minus 1, 0, 0, 1. Minus 1, 0, 0, 1. So, and the answer is minus 3, 7. So I suppose here I'm going to have to multiply these together. My preference is not to, but I'm going to have to, and then I'm going to have to worry about inverse matrices, I think. So if I just times those together, I get 1, I get, I'm just doing this times this, and this, I think that's a 0, I think that's a 0, and then 0, I think that's a minus 1, times by the AB equals minus 3, 7. And you can see what I need to do really is I now need to move this onto the other side, and when it moves over, it will become the inverse. It will be the inverse of 1, 0, 0, minus 1, times by minus 3, 7. And you'd be able to type that into your calculator, no problem. I'm just going to do it here now. Determinant of this is minus 1, minus 0. So that's minus 1. So when I do this, it's going to be minus, and I switch these round. Oh no, that should be a 1. And I change the signs, but they're both noughts anyway, so it makes no difference. So let's multiply these out. What do I get? It's a minus whatever I get. So minus, that's 3. And that's 7. So that sounds to me like it should be minus 3, minus 7. Let's see if that's what they agree. Yeah, that's what it agrees. So make sure, I repeat, you could have done that on your calculator, no problem. You didn't have to do it yourself. Determinant's an important idea. Look, my determinant then was minus 1. And actually, if you went back and looked at it, it said it was a reflection. So if the determinant is minus 1, it will always be a reflection. If the determinant is 1, it will be a rotation. Or at least the determinant we know of a rotation is 1. That's probably a better way of saying it. And if it's k squared, I know it's an enlargement. So there's a couple of things I can look for. Determinant tells us more than that, though, because it tells us something about the area. And this is something here. It says the area scale factor is what this tells us about. Probably easiest to see this in an example. So the unit square is transformed by this matrix. Find the area of the new image. Now, first of all, the unit square is 1 by 1 by 1 by 1. You can see it's got an area of 1. So bear that in mind. What's the determinant of this matrix? It's 2 minus and minus 1. So that's 3. So this is the area scale factor. It basically tells me my new area, I shall write new area, is the old area times by the determinant. So in this particular case, it is old area is 1 times the determinant is 3, so therefore it's 3. Here's a picture, my original unit square. I do my stuff with it. I get my new matrix with it. That, it looks horrible, doesn't it? Has that got an area of 3? Well, I suppose I could work it out because it sits quite happily in this box, which is 3 wide by 2 high. So the total area of the total box, this box here, is 6. But you'll notice I've lost a half a square. I've lost, well, that's actually add up to 1, and so does that. That's 2 squares, 2.5 squares. Sorry, a half, and 1 and 1. So I lose 3, so I reckon it has got an area of 3. So you'll have to take my word for it. I've done it rectangle minus 4 triangles, which is basically what I just talked about. That's got an area of 3. Why is the area equal to 3? Well, it's this thing I was telling you about. You get this determinant, which is 3. So I've done it in a slightly different way to the way the PowerPoint does it. But you get to the same idea. If you work out the determinant, you'll get your new area. And that's the formula which I wrote down for you. Other problems then, we've got a parallelogram with area of 4. Okay, fair enough. It's transformed by this matrix. Well, we just find the determinant. What's the determinant? The determinant is 4 minus and minus 6. Well, that's 10. So my new area will be 4 times 10, which is 40 square centimetres. And there it is, 40 square centimetres. So that's what we're going to do in class. This actually says questions 10 and 11. It's all the questions we're going to do because I'd already split this into 2 in a previous lesson. So we're going to do all questions from exercise 3B, and I think that's quite a nice little topic. But the tricky bit, of course, is learning all those different and quite similar rules for the different transformations that you're meant to know. And the mere fact that I put them on a page like that tells you that, yeah, good luck. You're going to have to learn them. You're going to have to sit down and remember them, work out ways to remind yourself of them. But in class, we will be doing, as I said to you, exercise 3B from memory. He said, not really remembering which one it was. Got there eventually, exercise 3B. So best luck.